try something again here. All right. So page 371, problem number 18. This is part A, using a graphing calculator. We know that the confidence level is 0.90. We know that X bar is 6.88. Sigma is 1.92. Sample size is 40. We go to stat. Test. Option number 7. We want stats, and then under sigma, it's 1.92. X bar 6.88. Sample size is 40. Confidence level is 0.9. We calculate, and we get this answer you see in red over here, 6.38 up to 7.38. $6.38 up to $7.38 is our confidence interval. All right. Now we're down here. So we generally want to decide confidence levels and the error E in advance. If you're doing some kind of practical or research application, like what size sample do you need, right? So here's how we find the sample size. Well, you guys, obviously you're in statistics now. You've had intermediate and college algebra, or at least you passed some placement test for that credit to get into the course. So what we do, we take that error, Z sub C times sigma over the square root of n, and algebraically solve it for n. And here's what you get. N equals, in parentheses, Z sub C times sigma divided by the error E, all of that squared. And that'll give you your sample size. And check this out. If you have if you find your sample size is something like 90.1, even if it's a little bit above, or 0.001 or something like that, you want to round up 91. If your sample size is exactly a number, like 90, you would just leave it 90, okay? But watch out for that, make sure you round up to the next level for sample size. Any questions on that? All right, so let's take a look at an example. I'm going to use the data from that same problem that we just did. I'm going to zoom in a little bit here. There we go. So again, this is number 18 on page 371. And this is part B. We already did part A. Find the sample size necessary for a 90% confidence interval. Or excuse me, 90% confidence level with a maximum margin of error of 0.3. So they tell us that the error they want is 0.3. All right. And remember that our sample size here was 40, but different information here, so we're going to get something else, right? All right. What am I doing? Erase. So we're doing this thing right here. We need the confidence, we need the Z value for a 90% interval, right? Z sub C. So Z sub 0.90. And on the table, that was 1.645. If you look at table 4B, right? So, what did I miss? Sigma. I forgot sigma. It was like 1 point something. What was it? 1.92. Okay. So that's all the given information that I need in order to calculate this. So my sample size is going to be, in parentheses, the Z sub 0.90, 1.645, I'm sorry, sigma. No, Z sub 6, no, that's right. How's it going to be? 1.645 times sigma 1.92 divided by our error that we want, which is 0.3. I'm just going to do that off the screen on a handheld calculator here. Squared, right? 1.645 times 1.92 divided by 0.3 in parentheses squared, and I get, what do I get? Here's what I get. $110.838, and it goes on and on, right? We're going to round that up to 111. So that's the sample size. Any questions on that? All right. Back out. And of course, there's your recommended homework for you. And here's section 7.2. Realistically, in real life, you don't know sigma because you haven't sampled everything in the population, right? So how do we estimate mu when sigma is not known? Well, what we do is, instead of using a Z distribution, we use something called a student's T distribution, the history of which is talked about at the beginning of this section in the textbook. And what happens is, if X is normally distributed with sample size n, then we can change X bar, instead of to a Z value, to a T value. And then we can either do it on the calculator or using a table in your appendix. I'm going to show you first the table in your appendix, and then we'll see how to do it on a graphing calculator. Now take a look at this formula over here. Remember when we did a X bar to a Z? We did X bar minus mu divided by sigma over the square root of it, right? Here we're doing X bar minus mu times S, the sample standard deviation over the square root of it. So what we're doing is using S, sample standard deviation, to approximate sigma. And in order to use this T table, you need to calculate something called the degrees of freedom. That is sample size n minus 1. All right, any questions so far? And again, we'll also see how to do it on the graphing calculator. On page 375, properties of the T distribution, I'm just going to give you a quick rundown of that. The T distribution's high point is above the mean, and it looks like a normal distribution, except the ends aren't as close to the horizontal axis. It's like it has fat tails, if you will, right? The tails of it. So then what we want to do with the confidence interval, it's going to be similar to what we did in 7.1, but instead of an error with a Z value and sigma, we're going to have that the error is going to be some T for some confidence level, T sub Z, times, instead of sigma, it's S over the square root of it. Other than that, you know, it's similar to what we did before. We're just using a different table and a T value instead of a Z value. Then we just do X bar plus and minus the error, and that's our confidence level. Any questions on that? All right, bear with me here. And let me bring up your appendix. I'm going to minimize that too. Yeah, okay, so we're going down, down, down to the T table. There's our Z table, there's our other Z table. Here's our students' T distribution table. All right, so here's table 5, students' T distribution. And again, if you're doing it by hand, you're going to be, or without a graphing calculator, I should say, you're going to be using this. So the degrees of freedom, remember that's n minus 1, right? The degrees of freedom are going down this column right here. When you're doing a confidence interval, you want that C right there. And what we're working with graphically is this first graph right here, where the shaded region is C, right? So what you do then is you go down to the appropriate degrees of freedom, go across until you find the appropriate level of confidence, and then see where it meets somewhere in the middle, right? Where do they meet? Just like using a Z table almost. So let's take a look at a problem as an example. I'll put it in this space right here. So 7.2. What I'm going to do, I'm going to do a problem that is on page 383. And it's problem number 14. Okay. Now, if you take a look at this in your book, or when you get a chance, they give you 20 values. The idea here, this is actual data, like so many of the problems that are given to you in the book. They went and found the average cost of a sleeping bag, and they sampled 20 different brands, I guess. So my sample size is 20. Then for part A, for these problems, they give you the raw data, but then for part A, they say plug the data into your calculator and verify that it has such and such for the mean and standard deviation, right? So part A is already essentially given and you don't have to plug it in your calculator. So in other words, they found that X bar was approximately equal to $83.75 based on that sample of 20 sleeping bags. And they found that the sample standard deviation was approximately $28.97. And then for part B, let me put a B up here. For part B, they want you to calculate a 90% confidence interval. Let me just double check and make sure I got that right and reading the correct problem. Yeah, they want a 90% interval. So notice that N is 20. I need degrees of freedom. That's N minus 1. That's 20 minus 1 is 19. So I need to find my T sub 0.90 value for this. Okay, so I'm going to bring that table back up. Readily. All right. So for degrees of freedom, this up. Degrees of freedom, we're going to go down to 19. So we're down here. Up at the top, we're going to go across to where C is 0.900. Notice here they do this, they write this stuff out for the thousandth place. We're going to see where they meet. They meet right here at 1.729. Any questions on that? By the way, on your quiz next week and on your test and on your final exam, when you're using a T table, make sure you get the correct degrees of freedom. because one of, you know how it's a foil answer, that type of deal on a multiple choice. One of the options would be that you use the degrees of freedom of 20 instead of 19. You forgot to subtract 1 from it. So watch out for that, okay? So we know it's 1.729. Right? So far so good. Now we're going to calculate the error. So the error, I'm using this formula right up here in the upper left corner. The error is your T sub C value, the T sub 0.90, which is 1.729, times S, which is 28.97, divided by the square root of n, which is the square root of 20. So I'm going to plug that into my handheld calculator here. Again, it's approximately, let me try to plug it in, 1.729, 28.97 divided by the square root of 11.2 approximately. Okay. And then I calculate my confidence interval, X bar plus and minus E. So that's going to be 83.75 plus and minus the 11.2. And I'll do that on my calculator. All right, so we're looking at $72.55 up to that upper limit, which is $94.95. Any questions on that? All right, let's take a look at this on a graphing calculator. So you should see a graphing calculator up here now. Just slide it over this way. So we're going to go to Stat. And we'll go to Tests. All right, this time I am looking for a T interval because we're using a T distribution. So I'm going to arrow down and find that. Here we go. T interval, option number 8. We'll press enter. And we're doing stats. And X bar was 83.75. Sample standard deviation, 28.97. Sample size here is 20. Confidence level is 0.9, which is already typed in there, or 0.90, however you want to say it. We'll calculate. And here we go. 72.55, you round it to the nearest cent, right? The hundredths place. So it matches up with our 72.55 up to 94.95. Any questions on that? All right, let's through that. And of course, that's the end of that section. Tech notes on what I just showed you on the calculator, page 377. Try problems 13 and 15. And I'm going to pause the recording. So back in chapter 5, we looked at a binomial distribution. And if you remember, with a binomial distribution, P and Q were the probability of success P and the probability of failure Q, which is 1 minus P, right? Well, we're going to use the P's and Q's again to form an interval for the population parameter for the probability of success, which is P. So what we're doing, we're going to use, you see this little P with the funny little mark over it, that's referred to as P hat. I mentioned that before in the previous class. So we're going to use P hat from the sample to estimate P from the population to a certain degree of confidence, a certain level of confidence, all right? Now, in the textbook, how do you calculate P hat? It's the number of successes R divided by your sample size N. And then see the Q hat right here? I made a typo, or I forgot to put something there. So make sure you do this. In fact, let me zoom into this. There we go. All right. Make sure you put a little hat over this Q right here. Q hat equals 1 minus P hat. Right? So then we're going to calculate our error, we're going to use a Z distribution. So it's Z sub C, the confidence level for Z, which is off of your standard normal Z table, right? Times the square root of P hat, Q hat divided by sample size N. The N is supposed to be under the radical side, just so you know. I spaced it down there this way. And again, we're going to calculate the error by hand. And then I'm going to show you how to do this on the graphing calculator. So take a look at example 6. I'm just going to do this example for you, even though it's already worked out. And it's on pages 390 and 391 in your textbook. All right. So here we go, example 6, bottom of page 390. I'm gonna give you a synopsis of what's going on here. So this is like out of a large university or something like that. There's 20,000 students in this example. Out of those 20,000 students, 800 were randomly selected. And they were given flu shots, right, for a particular type of flu. Totally at random, I picked this in the times that we're living in. Isn't that weird? Anyway, what are we at? So 800 of the students were given shots. All 800 of them were exposed to the flu. Out of those 800, 600 did not get the flu. So the shots were successful for 600. So that's R, your number of successes. Okay. And then they want you to calculate, let me make sure of the interval. They want a 99% confidence interval. Calculate a 99% confidence interval for P, the true population proportion of successes. So we have to find the error, and then we're just going to do P hat minus the error and P hat plus the error, right? Now we're using a Z table, which at this point, you guys doing it by hand, I think I've covered that enough, right? So if you look at your Z table, that's table 4B for the confidence intervals or confidence level. This turns out to be 2.58. Right? So I need to calculate P hat. That's 600 over 800. That turns out to be 0.75. And then we need to do Q hat, which is 1 minus P hat, which is 1 minus 0.75 or 0.25. So I found P hat and Q hat, right? So now I have everything I need to calculate the error. And in your book, notice they use approximately equal, right? So the error is approximately equal to. Your Z sub C value was 2.58. Oops. 2.58. You have to write it. There we go. Times the square root of. And then P hat turned out to be 0.75. Times Q hat turned out to be 0.25. All of that divided by n, which is 800. And on your calculator, you plug that in. You get approximately 0.0395. Okay. Any questions so far on that? All right. So now we're ready to find our error. I'll switch colors for that. So P hat plus and minus the error is going to be, what was P hat? 0.75 plus and minus the 0.0395. And if you plug that into your calculator, you're going to get 0.71. Up to 0.79. So we're 99% confident that P, the proportion of successes, is somewhere between 0.71 and 0.79. Any questions on that? All right. Choosing the sample size. And we saw something like this previously. We know that the error is Z sub C times sigma over the square root of n, right? So again, if you solve that algebraically for n, you're going to get n as Z sub C times sigma divided by the error E in parentheses squared. All right. Note this. If you don't know sigma, when you're trying to calculate a sample size like this, do a pilot study of size greater than or equal to 30, and then use S as an estimate. In other words, you're working in that central limit theorem concept that we saw in a previous chapter. The sample size greater than or equal to 30 means you can assume the distribution is approximately normal, right? I'll let you take a look at example 7 yourself. Here's another thing that we'll need to be able to do. Sample size for estimating P hat, which is R over N. How do you calculate that sample size? You're going to, if you have some preliminary estimate for P, you're going to use sample size equals P, probability of success, times Q, probability of failure, times in parentheses squared, your Z sub C value divided by the error. So like in the previous, in the first section, 7.1, where we saw, given certain information, what sample size do you want for a certain amount of error? That's if you have a preliminary estimate for P. If you don't have a preliminary estimate for P, it turns out that n times, or it turns out that p times q, that p times 1 minus p, the largest it ever will get is 1/4. Because if probability of success and probability of failure are both 1/2, 50-50, right? 1/2 times 1/2 is 1/4. That's where that comes from. And so for problems where it's asking you to find the sample size, which I'm going to do one of those and then we're going to be finished, make sure you're using the correct method. Does that make sense? Any questions on that? All right, let me give myself some working space here. That should be sufficient. And let me find the problem to work for you. 7.3. I would pause for flipping pages, but sometimes when I do that, I forget to turn the recording back on. All right. Actually, I said look at examples. Yeah, I said look at example 7. Give me just a sec. This is, let's do problem. Problem number 10 on page 396. Okay. So here's the given information. What is the minimal sample size needed for a 99% interval? So we want to be 99% confident. We have a maximal margin of error of 0.06. Part A, if you have a preliminary estimate for P of 0.8, and then part B, we'll just do when I get to part B, right? It's a two-part, part A and part B. So notice here, that was a bad decimal. Notice for part A, we have a preliminary estimate for P. That's this first case right here. So here's what we're going to use. So I need to find Z sub C. And I believe we just did that, and it's 2.8 or 2.58. Let me just verify that real quick here. Oh, I'm good. It is 2.58. All right. So we're going to do n is going to approximately equal P 0.8 times 1 minus 0.8, 1 minus P, that's 0.2, right? Times Z sub C is the 2.58 divided by the error that we want is 0.06 in parentheses squared. And I'm just going to do that on my handheld calculator again here. All right, here's what I get. It's 295.84. Now, if it was directly on 295 on the spot, we keep 295. But because it's a little bit more, regardless of how little more, we need it to be 296 to be safe. Right? Watch out for that rounding up. Any questions on that? All right. Part B. What if you don't have a preliminary estimate for P? Then we're going to use this to calculate. So n will equal 1/4 times the 2.58 divided by the error 0.06 in parentheses squared. Look at the difference here. This turns out to be approximately 462 times 0.2 or 0.25, 462.25, which we're going to round up to 463. It's a big difference when you know more information. You don't need as large a sample size, right? Which makes sense. Any questions on that? All right, let's go back. Sorry to go back, but I want to go back to the future. Let me show you this on a graphing calculator, okay? Because I don't think I showed you how to find the interval on a graphing calculator for this. So let me just make sure that I cover that, and then we are done until next Monday, right? Press stat, go to tests. Yeah, I can't remember if it's shorter to go up or down with this. Here's what we want. Option A, 1 proportion Z interval, 1 prop Z int. All right, we'll select that. For, oh yeah, so check this out. On your graphing calculator, they have X. In our textbook, they use R. There are other textbooks where they actually use X, but R is the number of successes. So that for us is 600. Sample size, 800. Confidence level for this one, we want 0.99. And we'll calculate. And let me just move this over. So compare that to the answers that we found doing it by hand. 0.71 up to 0.79 rounded to the hundredths place matches right up. Any questions on that? All right. I will stop sharing. Have an excellent weekend, and I'll see all of you next week. Be safe out there.